Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. What did we discuss yesterday? Yesterday we discussed about the carbohydrates, amino acids, hydroxy acids and terpenes. What are the target molecule and how we will get as a precursor. So that type of the brief introduction about that we have seen. So today we already studying this, the Chiron approach, what type of the Chiron approach the organic chemist should keep in a mind, and that is how it is benefited in this area, or there are the various aspects we are learning. So in that the concept of chiral templates and the chirons, wherein the carbon skeleton is the chiral precursor. Here the concept of chiral templates, chirons, wherein the carbon skeleton is the chiral precursor. Chiral templates means while the this building, before constructing this building, there are so many raw material. One of the material is used as a brick, and while preparing or while making that brick, the worker is one what we can call it as a one definite shape of that shape is there, and pouring the material over there, it attain that particular, and brick is prepared, and that brick is used for the construction of such type of the big building, and that is the meaning of that chiral templates. Though this is a chiral template, and as we know that chiron word is coming from the two words, one is a chiral and second one is a synthon. So today what we are going to learn stereochemistry, stereoelectronic effect and conformation in the carbohydrates, because here we are going to use our approach. We are keeping the approach of carbohydrates. How? Because there are 6 compound we are going to learn their retrosynthesis and how they are synthesized in the laboratory. Number 1, propanediol, then RS epichlorohydrin, then minus multistatin, then pentamycin, then shikimic acid. These are the 6 compound we are going to actually we are going to learn their retro, how the Chiron approach is that will help. Before that we are studying how we are going to keep the Chiron approach here there in actual synthesis of those molecule, and for that we are we must need, these are the some of the terminologies, or what we can call it as important point to arrive that synthesis, and therefore that, and we know that stereochemistry is a branch of chemistry that deals with the study of arrangement of or the orientation of the atom in a space, or study of 3-dimensional structure of that organic molecules. And as we know that even though it's a very small molecule, but the arrangement of that atom in a space is a very different one, and therefore it is necessary to study its stereochemistry and what kind of the stereoelectronic effects were there. And as we know that for the carbohydrate, and everybody knows that the simplest definition of the carbohydrate is that, the simplest definition of a carbohydrate is that it is a polyhydroxy aldehyde or ketone capable of existing in a cyclic or acyclic form. This is the simplest definition of the carbohydrate. What the simplest definition made here, it is a polyhydroxy. Poly means different, poly means more than 2 are called as a poly, or 3 or hydroxy groups are there, and therefore the simplest definition of the carbohydrate is that, what is the carbohydrate? It is a carbohydrate is a polyhydroxyaldehyde or ketone capable of existing in cyclic, cyclic as well as acyclic form. So that type of the thing is called as a carbohydrate, because this carbohydrate may present, and while studying their carbon framework, as we know that, and the asymmetric carbon, so these are the chiral precursor generally used for the synthesis of these drugs, and therefore it is necessary, it is essential to study their stereochemistry and the stereoelectronic effect, like as anomeric effect, or if the substituent, whether they are what we can call it in an equatorial position or the axial position, what is going to happen. So that type of the conformation, again, conformation means what? Just by rotating the mainly as a 6-membered ring or 5-membered ring, then the 6-membered ring, like as a in a cyclohexane, you might have studied the stereochemistry, that cyclohexane prefer to stay in a chair conformation, because chair conformation is more stable than the board. So that type of the thing we are going to learn here. And in this regard, R plus or S minus glyceraldehyde, one is the simplest carbohydrate is a glyceraldehyde. Glyceraldehyde used as a reference compound in the carbohydrate. It has a 3 carboatom carbon skeleton. The carbon framework is present. There is a 3 carbohydrate, or sometimes it is known as a triose. Tri indicate as a 3, and OS indicate as a sugar unit is there. So carbohydrate in more evolved system, a carbohydrate, an assembly of a carbon atom with predisposed sense of chirality, each of which can be manipulated or used as an stereochemical reference in an absolute sense. Absolute sense, I already told you, D and L, capital D and capital L are the relative configuration, whereas R and S are the absolute configuration. And an understanding of the factor that control such process, and the knowledge of structural and the stereochemical requirement and their consequence are basic tenets for utilizing carbohydrate in organic synthesis. Taking D-glucose as an example, it can be seen that the acyclic polyhydroxyaldehyde form is in equilibrium with the 2 cyclic forms. Scheme number first over here. Let us see the scheme number first here in the carbohydrates. Let us see, here is a scheme number first over there. There are different scheme we are going to learn here. Let us see as a scheme number first one. So here, as we know that the carbohydrates are generally present in these forms. Let us see here. This is one of the form of the carbohydrates. Let us see, start from here. So this one O, 6-membered ring, as we know that this is a 6-membered ring of that carbohydrate. Look at this, is a carbon skeleton over there, this one, and which is, and here one group which is above the plane is written over here, and HO, and now other side there are OH. We know that one OH is below the plane, another OH also below the plane, one of the OH above the plane, and here this OH is below the plane, like this. And that as we know that suppose this is one of the structure, and that structure is generally present in the what we can call it as a, this one is a exists. Here is a small arrow indicate that there is a open chain compound, as we know that open chain compound is a this one. This is a CHO, there is a OH, then OH, then this 3 OH on that OH. Look at this is a 1, 2, 3, 4, 5 and 6. This is a open chain structure of D-glucose, right? This is a structure of D-glucose. CHO, OH, OH, OH. So this is a structure of D-glucose, and this can be, we can show this interconvert. This structure may exist in this form like this. This is the form we can show here, OH, then HO, this one, and now there will be a one OH here, again this one OH and one OH should be there, and then this arrow shown here, and one is a small arrow that is which is this one, that is a present. This one is a present is a greater form. This is a 6-membered ring. These are the various form, because this is a cyclic compound of D-glucose, and this is a cyclic form of glucose, D-glucose, and this one. And now when they form, or this can be written like this. While studying as a carbohydrate, we will see the details of this, but here just remember how we can draw these structures. 1, 2, 3, 4, 5 and 6 over there. This the HO, then there is a hydrogen atom OH group 1 over here, then here OH, this OH, and here another OH, and then CHO group. This is a CHO group, or this can be written as like this. This can be written like this. Here is a OH, then here also OH, and this can be written as here OH, OH, and here is again as a OH, OH, and here CHO, right? Here is a CHO. These are the various form of this compound. One structure we can draw in a various form. This is a open chain which containing, and according to our definition, what is that? It is a polyhydroxyaldehyde are the ketone capable of existing in cyclic or acyclic form is known as a carbohydrate. So that is the definition of that, and this is a open chain compound, as we know that, and the molecular formula of glucose is a C6H12O6, right? Number of carbon atom are 6. Look at here, 1, 2, 3, 4, 5, 6, and 12 hydrogen atoms are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and this 12. And how many oxygen atom are there? Look at here, 1, 2, 3, 4, 5 and 6. So this is a 6 hydrogen atom over the 6 oxygen atom over there. And now what is this arrow? These are the equilibrium arrow. this is exists in a major, and that's why long arrow is shown, and the open chain is only as a 0.02% present in the solution, and like this. And this is a 5-membered ring. The 6-membered ring is a majority form, and the 5-membered ring is a minor. Again, but as compared to the open, 5-membered ring exists in a majority form, whereas this open chain is again one more structure. This structure we can draw in a this way also, in a chair form also we can show this structure. There is an oxygen atom, this is a chair form. This compound we can draw like this in a chair form, and all the except the anomeric, this carbon atom is known as an anomeric carbon atom, because here OH is below the plane, and that's why it is known as alpha D glucose. When OH is below the plane, so that type of the thing is called as a alpha D glucose. Now remember, those hydrogen atom on the right hand side, they are below the plane, and those are on the left hand side. Look at, here is a one left hand side, and therefore it is on above the plane, we can remember. So that is a thing over there, right? So now here this OH is at axial position, and rest of the compound remains in the equatorial position. This is a OH, then here OH, then OH, and here also as a OH. They are all present in the equatorial position except the anomeric, except this one. At one position, this position is called as a anomeric carbon atom, means where the configuration of this alpha and D are the mannose and the fructose, what we can call it as a glucose. They are the anomers of each other, anomer, epimer. So that type of the term we will learn while studying as special carbohydrates are there. So this is a structure of alpha D glucopyranose. This is a structure of alpha. Why alpha? Because it is below the plane. Alpha D glucopyranose. Glucopyranose. This is the name of this compound. And now here, how many chiral center you can see over here? 1, 2, 3 and 4 chiral centers are there. Look at these 4 chiral center, means there are the 4 secondary hydroxyl groups are there. Only one primary hydroxyl. This below one is a primary hydroxyl group, you remember there. And now if you see over here, the structures are generally shown like this, dot dot dot. Then here is a OH and here is a H. This is a thing we can, here again the dash dash vertical is a dash dash. This is a chiral number 1, right? Chiral number 1. Then carbon number, this is a carbon number 1, this is a carbon number 2. Another one we can write here, another way of showing as a carbon number 3. So we can show here like this. One group is like this. Here you will show this way also. Here is a hydroxy group on left hand side and hydrogen atom on a right hand side. This is a carbon number 3 over there. Then again carbon number 4 we can show. This is a 1, 2, 3, 4, 5 and 6. At carbon number 4 we can show like this. Carbon number 4 we can show like this over here. Hydrogen atom. This is carbon number 4. At carbon number 4 OH on the right hand side and H on the left hand side. Then you can show the carbon number 5. So you can show the carbon number 5 also, OH on the right hand side, hydrogen on the left hand side, and there this one OH. This is a carbon number 5 and this one is a carbon number 6. I am showing this one is a separately so that you can clearly identify there are the 4 chiral centers are there. Look at what, and again remember what type of the configuration generally present in the carbohydrate. What do you think? There are the 4 chiral centers are there. 1, 2, 3, 4, right? And here always remember, suppose let us see here what type of the configuration of this compound has. Let us see here, give the priority number here 1, right? And it one is a 2 and this one is a 3. 1, 2, 3. This is a S type, but hydrogen atom which is present at a horizontal position, horizontal. Therefore, S is changes to R configuration, right? And therefore, if remember one trick, remember here when OH is on the right hand side, that that conformation that shows the R configuration. Let us in glucose you can write as a 2R, then 3S, then 4R again, and 5R like this. These are the configuration. If you count, so you will find that just by remember as this trick or as we know that number. Look at 5. Suppose here is a 1. Among these two, which one is getting as a highest priority? This one, 2, and this one is a 3. 1, 2, 3. Look at here what type of the S changes to R, right? And here look at in this case third is a why we are getting as a look at here is the first one and the second one is a this one or this side definitely aldehyde there, so it is the second and this is the third one. 1, 2, 2, 3, that is a R configuration, but hydrogen atom is a horizontal and therefore it changes into as a S, and that's why these are the configuration. These are the general thing you have to remember over there. Now the 6-membered pyranose ring is favored over the 5-membered ring. Just now we have seen this is a 6-membered ring and this one is a 5-membered ring, but that 6-membered ring is according to as a bare strain theory, 6-membered ring is generally is a there is a no minimum strain is there or steric strains are there, and that's why it is exists in a majority form than the over the 5-membered ring. So that is there. And in the C1 conformation, alpha D glucopyranose has all its substituent equatorial except for the anomeric position, and I just now told you that this is called as the anomeric carbon. Anomeric means what? Anomers or the anomeric where the configuration is a change, and if OH is here at a equatorial position, look at and remember in a 6-membered ring, if you remember your cyclohexane, the bulkier group prefer to stay at equatorial position. Why in a equatorial position? Because there is a no 1,3 diaxial type of the interaction or Gauch interaction is absent over there, and due to this reason the bulkier group prefer to stay at a equatorial position, except this hydroxy group which is at anomeric center present over there, and all other hydroxy group are present at a equatorial position. So that is there, and this form of D-glucose can be conveniently manipulated as a 6-membered cyclic derivative, much the same way as a cyclohexane derivative, with allowance made to the stereoelectronic consequences of replacing a ring carbon by an oxygen atom. Under the constraint of ring forming reactions, D-glucose can be used as a 6 or 5-membered structural entity. For example, methyl alpha D-glucopyranoside readily forms a 4,6-O benzylidene acetal derivative of the trans-decalin type you might be knowing decalin type, which is a crystalline and an extremely versatile starting material. Versatile, and as we know, the versatile precursor or the versatile starting material. Now let us look at the scheme number second, how we can get that versatility of that starting material. That's why we are learning this in detail. See the scheme number second now here. Here is a scheme number second over here. Let us see here, as we know that it is a D-glucose, right? D-glucose over here, and this D-glucose, when treated with first one methanol, as we know that MEOH in a catalytic amount of acid, and second further treated with this benzaldehyde PHCHO in a acidic medium. As we know that it is a protecting group at 1,3 position, right? As we know that in a protection and deprotection, there acetone is used for the protection of the 1,2-diol, whereas benzaldehyde in presence of the acid is used for the protection of 1,3-diols, that we already learned. So that is that thing, whatever we are learning, we are going to apply here, and therefore what type of the structure you are going to get over here. So this is a structure you are going to get over here. Just now we have seen D-glucose is present in the chair form like this, and this then axial OH D-glucose get replaced by OMA here, which is present at axial position, and other hydroxyl group which are present in the equatorial position, and this 1 and 3 position, that hydroxy group, here we can draw this structure over there, and then here this, I think not this one, and here you can write as a this something not looks chair conformation is like this, okay, and then pH which is present at a equatorial position. This is a structure when we are adding methanol, what in a D-glucose they get replaced by here specifically, and 1,3 get protected, and then you can treat this compound with number 1 with that modify this one, modify. Second one, deprotection, because it is a protection process, deprotect it, and third one, it is modified again, modify. What do you get after modifying everything? So you are going to get the compounds like this. You will get here this compound, this one, and everything is modified. Here just OMe. Here you can write this one is a, I think A, then B, then C, and then here you can write as a D. This group in a D-glucose, that is shown like this, and this we can write this way again, 6-membered ring like this one, and there will be here D you can write, and here again OMe, and here it is not assigned. This clearly indicate as a that zigzag line clearly indicate that whether it is below the plane or above the plane, that is not assigned that, and that's why it is shown here. And here is a B, and here is a B, and here is a ABC group is there, and that is a D. So in this way we can modify this, and now this glucose, suppose further treated with this one, suppose treated with acetone, right? Acetone in presence of H plus, and this can be protected as a 1,2, for example in case of the 5-membered ring. So let us see here 5-membered ring specially, and here we are getting O, this get protected, and here also O and O, it get protected, and here only one OH remains there. OH, it is not in a vicinity, and therefore it is shown as a like this OH, right? And then after that, first one is a modify. Second one will be the deprotecting. Second one, deprotect, and after that, what do you get? You are going to get this one. After deprotecting, you will get over here this structure, and this HO and this HO get free over here, and this here you can write this one is a B, and this still protected over there, and then it can be modified, or this can be removed. What do you get? You can get this type of the compound. No, not this. Still it is a protected, and this is a B, and here OH. After the modify, we will get this one, or this can be converted into this one. This way we can write 1 2 3 4 5 6, 1 2 3 4 5 6, and there CHO. Then here you can write A, here you can write B, here you can write C, and here OH, and here you can write as D in this way, or this can be converted into this one also. And another way, if this one is treated with RSH thiol, RSH in presence of H plus, what do you get? This glucose get protected over there, and you are going to get here like this SR, then SR aldehyde group, then OH, then HO, then 1 2 3 OH on what we can call it, on a right hand side like this, and this we can write in this way also, 1 2 3 4 5 6. So here HO 2 3 4 5 6, 1 2 3 4 5 6, maybe as a here SR, this one is a SR, and here this is a OH group, here also as a OH group, and this will also as a OH group. In a previous scheme also we have seen, and here is a one of the hydrogen that goes below. So this is a structure, or if you modify it, or you can modify it, what do you get? You get a cyclic chain or cyclic derivatives. You will get a cyclic chain as well as cyclic derivatives, or you can get cyclic derivatives. This is a scheme number 2, and in this way we have get this. So in the presence of acetone and acid catalase, D-glucose gives the highly crystalline 1256 isopropylidine, this one, propylidine alpha D glucofuranose, another cornerstone in organic synthesis from carbohydrates. And finally, D-glucose can be trapped as the kinetics acyclic derivative by treatment with the thiolane acid to give the corresponding dialkyl dithioacetal this way. So these are the three different way we can get the precursor as a this way. Now we can consider a 6 carbon acyclic chain for a synthetic purpose. Of course, this option is in a principle always available with the modified pyranose and furanose forms. Hence, the advantage of achieving stereo control in a cyclic system indirectly by prior manipulation of acyclic or cyclic derivatives, and thus depending on the structural requirement of the desired precursor, one can make the proper choice of starting material derived from a given sugar. In general, the same rule for obtaining different ring forms or the acyclic derivatives apply to other sugars as well as the identical stereochemical and conformational characteristics have to be appreciated. For example, ketone will usually lead to the dioxane ring, but aldehydes can give dioxazolone or dioxane ring. Compare D-glucose and the D-galactose. As in cyclohexane derivatives, non-bonded interaction are in general destabilizing in a pyrazone derivative, and the preference of an electronegative substituent at the anomeric carbon atom, as we know that in the anomeric carbon atom, this is the anomeric carbon atom here, and how it can be modified. So remaining thing we will see in the next lecture. I think let us again revise these things are there. What this is a D-glucose. D-glucose, as we know that it is a open chain D-glucose, or it may be present in the more percentage of cyclic in the chair per form, and when it is treated with methanol OH, that axial OH group get converted into as a this ether type of the ether is formed, and then PSCHO, it is known for the protection for the 1,3-diol, which is protected like this, and then modify deprotection modify, we will get as this type of the. So a final goal to achieve the precursor in any way so that we can synthesize our target molecule. I think with this let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.